Virtualized Radio Access Networks, or vRANs, will become the spearhead of next-generation mobile systems beyond 5G. Through a series of initiatives, such as O-RAN, vRANs will provide multiplexing gains via centralization, agile software development techniques, and cheaper deployments through standardization and commoditization. We present a machine learning-based algorithm that operates in O-RAN's non-real-time RAN intelligent controller or non-real-time RIC. The near-real-time RIC constantly collects contextual data from the base station underneath through E2 interface. Every interval, which is 5 minutes in our setup, our learning agent collects aggregated context data from the near-real-time RAN controller through O1 interface, computes a policy, and enforces this policy using A1 interface. We consider the problem of maximizing network capacity subject to a hard constraint on the virtualized base station's power consumption. To this end, we collect information about network load demand in both uplink and downlink, and channel quality estimations on both directions. We aggregate all this data together to build a context vector, which we use a representation of the state at the current time. In turn, the action space consists policies concerning use of modulation and coding schemes, amount of time that the base station can transmit, transmission power, for the downlink case only. Our goal is to maximize the network reward, which encodes a network capacity utility, subject to those available action, context pairs within our budget constraint. As we show in our paper, our context action reward space is highly nonlinear and non-monadic. Moreover, the objective function values of two different nearby actions are correlated. This motivated us to employ a Bayesian online learning mechanism, which is data efficient and lets us encode hard constraints. The testbed used in our demonstration consists in one base station implemented with SRS-RAN, an open-source 3GPP-compliant base station, virtualized into Linux containers and using a software-defined radio board to transmit and receive data over the air. We use a power meter to measure the power consumption of the base station and use a standard traffic generator to send data in both uplink and downlink directions. In our demonstration, we emulate daily network load patterns collected from a real base station in Germany over the scope of 5 days. We will modify the power budget of the base station every day to see how our algorithm reacts. For the sake of convenience, 5 minutes of real-time are represented into 5 seconds in our visualization tool. We track the evolution of our system in this dashboard. At the top, we present the uplink and downlink configuration policies that the learning agent recommends every interval, which is 5 seconds in our demonstrator. At the left, we show the real power consumption of the virtualized base station with the red area. In green, we simply notify the current power consumption limit. At the right, we show the network load dynamics in yellow, and the achieved network throughput in green. Finally, at the bottom, we plot the system reward over time. Let's get started with the actual demonstration. At the beginning of day 1, we set our power budget to a high value so the algorithm can learn a wide set of context action pairs. At this moment, our learning agent has no knowledge whatsoever about the system. As you can see, the algorithm takes some random actions, which render bad performance at the very eerie intervals of the day. However, after just a few iterations, the algorithm begins making high-performing actions, maximizing uplink and downlink throughput. Let's speed up till the end of the first day. At the beginning of day 2, we reduce the power budget, which limits the action set to a safe set that guarantees meeting our power constraint. As you can see, as a result of the new constraint, our learning agent chooses reduced transmission power settings that result into reduced downlink throughput during the moments of peak load. It is interesting to observe that, with this power constraint, the uplink performance remains at its maximum. At the beginning of day 3, we reduce our power constraint a bit more. As a result, our algorithm reduces the downlink transmission power even more to respect the power constraint. Although these decisions cause throughput loss, the algorithm manages to maximize the overall spectrum capacity that respects our tight power budget constraint. Note how the uplink performance remains at its maximum. Again, at the beginning of day 4, we reduce our power constraint even more. Not surprisingly, our algorithm chooses even lower transmission power settings to respect our power budget. However, in this occasion, in order to avoid collapsing downlink capacity, the algorithm trades off some uplink capacity by choosing some conservative uplink policies too during the moments of peak demand. During the final day of our demonstrator, we reduce our power budget a bit more. As a consequence, the algorithm is limited to a small set of actions that can maximize network capacity while respecting our tight budget constraint. We can observe that now the algorithm is forced to sacrifice both downlink and uplink capacity substantially. We have, in conclusion, demonstrated the feasibility of integrating Bayesian learning mechanisms into vRAN intelligent controllers, opening the door to even more network intelligent mechanisms that will make happen the next generation of mobile systems. You can find more details on the design of our algorithm and a rigorous analysis in the paper that you can see in the slide. Thank you for attending.